Right now, as you're listening to this, a small machine, about the size of an old car, is hurtling through the silent, crushing dark of interstellar space. It's more than 25 billion kilometers from Earth, a distance so vast that a message sent from home, traveling at the speed of light, takes nearly a full day to reach it. In early 2025, it became the first human-made object to be one light day away from us, and it's only getting farther. The environment it's flying through is one of profound, absolute hostility. The background temperature of the universe, the faint echo of the Big Bang, is a steady 2.7 Kelvin. That's just 2.7 degrees Celsius above absolute zero, the theoretical point where all atomic motion is supposed to stop. In an environment like that, anything should freeze solid. Any machine should have seized up, its electronics dead, its power source inert, becoming nothing more than a frozen coffin of technology. But this machine, Voyager 1, is still alive. And here's the most astonishing part. This isn't some cutting-edge probe, it's a relic, a piece of vintage tech launched way back in 1977. Its onboard computers have less processing power than the chip in your car's key fob. It was launched before the first CD was ever pressed, before the internet as we know it even existed. And yet, for nearly half a century, it has survived. It still gathers data. It still communicates with its creators on a tiny blue planet it can no longer even see. So how does a machine built during the Ford administration, a product of the disco era, survive the most hostile environment we know? Why hasn't it frozen into a block of dead metal? The answer is a story of profound engineering genius and a deep understanding of physics. Because the real question isn't just about the cold. The real question is, do you understand what cold truly means when there's almost nothing there to touch you? Here on Earth, our experience of cold is immediate and aggressive. Step outside on a freezing day and you feel the cold bite your skin. That bite is a physical process. It's the result of trillions upon trillions of super-fast, super-cold air molecules slamming into your body. In each of these microscopic impacts, the air molecules steal a tiny bit of your body heat. It's a relentless robbery, a process called conduction through direct contact, and convection when that heat is carried away by wind. This is why a windy winter day feels so much colder than a still one. It's also why touching a piece of metal, a fantastic conductor, feels so much colder than touching wood at the same temperature. One is just way better at stealing your heat. Our entire intuition about cold is built on this idea of heat being actively stolen from us. But in the space where Voyager 1 travels, our surroundings barely exist. Interstellar space is one of the most perfect vacuums we know of. Down here at sea level, a single cubic centimeter of air, about the size of a sugar cube, contains roughly 30 quintillion molecules. That's a 3 with 19 zeros after it. In the interstellar medium where Voyager roams, that same cubic centimeter might contain just 5 atoms. Not 5 quintillion, just 5. The difference is almost impossible to wrap your head around. With so few particles, there's virtually nothing to collide with the spacecraft. There is no wind to carry its heat away. There is no matter to conduct the warmth out of its systems. The aggressive, heat-stealing cold we know on Earth simply doesn't exist out there. So, if a spacecraft can't freeze through conduction or convection, how does it lose heat at all? The answer is a third, more subtle process: thermal radiation. Every object in the universe with a temperature above absolute zero emits energy as infrared radiation. It's a type of invisible light.
You are emitting it right now. Your chair is emitting it. The Earth itself glows in infrared. This radiation is the only way heat can travel across a vacuum. It's how the sun's warmth reaches us across 150 million kilometers of empty space. So, for a spacecraft like Voyager 1, this is the only way it can cool down. It slowly, gently radiates its internal heat away into the void as invisible light. The best analogy is a thermos of hot coffee. If you leave a regular mug of coffee on your counter, air molecules will relentlessly bombard it, and the coffee will be cold in under an hour. But if you put that same coffee into a high-quality vacuum-sealed thermos, it stays hot for hours. Why? Because the vacuum between the walls prevents heat loss by conduction and convection. The only way for the coffee's heat to escape is by slowly radiating away as invisible light. Voyager 1 is that thermos floating in the greatest vacuum chamber imaginable. The problem of space isn't an aggressive cold trying to get in. It's the slow, passive, and endless bleeding of its own precious heat out into the void. To survive, it doesn't need to fight off an attack. It just needs to generate more heat than it loses. And it has to do it for 50 years, billions of kilometers from the sun, where solar panels are just useless frozen wings. The solution, therefore, couldn't come from the sun. It had to come from within. The heart of Voyager is not a computer or an engine. It's the steady, predictable, and incredibly powerful process of atomic decay. The spacecraft is powered by 3 devices called radioactive thermoelectric generators, or RTGs, and they are the single most important reason Voyager is still alive. An RTG is basically a nuclear battery with no moving parts. At its core is a ceramic material containing pellets of plutonium-238. This specific isotope isn't the kind used in weapons. It's an alpha emitter, meaning that as it decays, it releases alpha particles. These particles can be stopped by a sheet of paper, but as they're absorbed by the surrounding material, they generate a tremendous amount of heat. When Voyager 1 launched in 1977, its 3 RTGs contained about 4.8 kilograms of plutonium-238 each. This material was slowly decaying, generating thousands of watts of thermal energy. But how do you turn heat into electricity in space, with no steam, no turbines, and nothing to break down? The answer is a 200-year-old discovery known as the Seebeck effect. This principle says that if you join 2 different conductive materials at 2 points, then make one hot and the other cold, an electrical voltage appears. Electrons, energized by the heat, flow from the hot side to the cold side, creating a current. The RTGs on Voyager are masterpieces of this principle. The decaying plutonium provides the hot side, heating the inner junction of hundreds of thermocouples to over 500 degrees Celsius. The cold side is provided by radiators facing the frigid blackness of space. This huge temperature difference drives a constant, steady flow of electricity. There are no parts to wear out, no combustion to manage, no maintenance needed. It is the perfect power source for a lonely machine on a journey of many decades. But here is the crucial, elegant secret to Voyager's survival. Electricity was only half the story. The process of converting heat to electricity in an RTG isn't very efficient. Most of the energy from the decaying plutonium, thousands of watts, isn't converted into electricity. It's simply released as waste heat. On Earth, this would be an inefficiency. In the frozen void of interstellar space, this waste heat is life itself. The RTGs act as Voyager's central furnace. This constant, reliable warmth radiates through the spacecraft's body, flowing through its structure and keeping the delicate electronics from freezing. The propellant lines for its tiny thrusters are filled with hydrazine that would freeze solid at 2 degrees Celsius, but are kept warm by this internal glow. Even the electronics themselves, with every calculation, generate a tiny bit of residual heat, contributing to the overall thermal balance. Voyager is a self-warming machine. It creates a small, habitable bubble of warmth in the infinite freeze, all thanks to the predictable, clockwork decay of a few kilograms of a radioactive element. It has a nuclear heartbeat, and that's what has kept it from succumbing to the cold. But generating heat is half the battle. You also have to keep it. If you look at any picture of the Voyager spacecraft, the most striking feature is what looks like gold foil wrapping. This has led to the common misconception that the probe